Yes. Merhaba değerli katılımcılar. Bir Profen Teknoloji Günlerinde yine sizlerle buluştuğumuz için mutluyuz. Ben Saadettin Avcılar. Yurt dışı tedarikçi ilişkileri görevini yürütüyorum. 3 senedir yapılmakta olan Profen Teknoloji Günlerinde Profen iletişim bünyesinde bulunan teknolojileri ve tedarikçilerimizin teknolojilerini katılımcılarımız ile paylaşarak ortak çalışma zemini bulmayı amaçlıyoruz. Bugünkü konumuz Orolia firması ile yer, zaman ve konum test ve simülasyon çözümlerinde inovasyon ile ilgili bir oturum gerçekleştireceğiz. Oturumu Orolia firmasından David Godwin, Robert Burke ve Lisa Perdue sunacak. Ben önce bir iki kelime Profen'den bahsetmek istiyorum. Profen 27 yıl aşkın süredir haberleşme teknolojileri, savunma teknolojileri, teleport ve uydu network hizmetleri, medya, yayıncılık, EPC ve yaşam bilimleri sektörlerine ürün ve hizmet sunan global bir şirkettir. Merkezi İstanbul'da bulunan Profen, Ankara, Konya ve yurt dışında Bakü ve İngiltere ofisleri ile dünya çapında yenilikçi ve yüksek uydu haberleşme teknoloji çözümleri sunmaktadır. Profen bünyesinde barındırdığı farklı grup şirketleri Profen İletişim Teknolojileri, Profen Savunma Teknolojileri, Profen Uydu Hizmetleri, Profen İnşaat, Profen UK ve Profen Yaşam Bilimleri ile ticari ürünlerden askeri projelere uzanan geniş bir sektör yelpazesinde uzmanlık ve bilgi sahibidir. Gerek yerel, gerekse uluslararası uydu data trafiği için servis veren Konya Teleport'u da ev sahipliği yapan uydu servisleri bölümü de grubumuz bünyesinde yer almaktadır. Sunumumuz İngilizce olacaktır. Kısa İngilizce açıklama sonrasında sözü önce Orolia firmasından David Godwin'e vermek istiyorum. Dear participants, we are pleased to see you again in our Profen Tech Days. I'm Saadettin Avcılar. I'm in charge of overseas supplier relations. We hope that by sharing technologies from our suppliers at the Profen Tech Days, which have been around for 3 years, we'll find common ground within the ecosystem. We are going to have a session with our guest, Orolia, to discuss about innovation in PNT test and simulation. David Godwin, Robert Burke, and Lisa Perdue from Orolia are going to present the session. Hello, David. Welcome to our webinar. It's over to you. Please tell our audience about Orolia and please present other speakers when your presentation is over.
Thank you, Saadettin, and it's great to be here, and thank you everyone for joining us. So I think Saadettin has already introduced us, but just quickly, I'm David Godwin, and I'm the Regional Sales Manager for Orolia, based in the UK, and I work very closely with Profen. And then obviously giving the presentation, we have Lisa Perdue, our Product Line Director for Simulation, and Rob Burke, our Business Development Director. I'll just briefly highlight the agenda for today's webinar. So what we'd like to do is basically start with an overview of test and simulation for PNT, or positioning, navigation and timing, discuss modern requirements and how there is a demand for going beyond simple GNSS testing to test a whole lot more signals, custom signals and other requirements. We'll discuss innovation in simulation and then introduce Skydel, which is our basis of all our high-end simulation, and it's based on what we call software-defined architecture. We will discuss this software-defined architecture and make a comparison with more traditional simulation and show how this new approach is more effective and gives much more kind of opportunity for innovation. That will lead into discussing Skydel and its unique capabilities. We'll end off with a couple of example use cases which will illustrate how this software and technology has been used to solve real applications and real problems. We'll finally round off with a question and answer session where we welcome you to ask any questions you have, and we'll be very happy to answer those and have an open discussion. I've got a slide 2, please, Rob. So briefly, I'll just introduce Orolia. So I'm not sure how many of you know Orolia. Orolia, we're actually much more than simply a simulation company. We're actually a global leader in resilient positioning, navigation and timing technologies. We have offices in Europe, North America and also in Asia. In terms of these 4 pillars, we start with resiliency, and actually we provide interference, jamming, and spoofing detection solutions for application using GNSS. And briefly, just mentioned, some people may not be familiar with the acronym GNSS. GNSS stands for Global Navigation Satellite Systems, which includes GPS, Galileo, Beidou, GLONASS, which are the 4 main global systems, but also the Indian NAVIC system and QZSS in Japan, as well as actually other signals, including SBAS and a few other signals we'll talk about. In terms of positioning, we actually provide emergency locator beacons for airlines globally, including sole source for Airbus for all their commercial airliners, as well as military and other civilian applications. And this also includes GNSS antenna solutions. In terms of navigation, we actually provide protection for navigation systems, rugged navigation technologies for mobile applications, and obviously test solutions for any navigation applications, which includes the simulation technologies, which we will be discussing today. And finally, actually, we are a global leader and been working for many decades in timing, so actually providing high accuracy timing technologies and atomic clocks, actually including the atomic clocks which are installed on the Galileo GNSS constellation, and also time and frequency ground masters, which are deployed in clocks for civilian and military applications all over the world. Next slide, please, Rob. And I think the next slide I'll be handing over to you, Rob, to dive into simulation in a bit more detail.
Definitely. Thank you so much, David, for kicking that off and getting us off to a good, solid start. I'd like to start off a little bit about talking about PNT test and simulation. And I think sometimes the best place to start is at the very, very, very basic overview of what we mean by simulation. So when we talk about GPS or GNSS simulation, if you look at the diagram on the right, really we're talking about starting at the satellite itself. And we create all of the satellites that David mentioned earlier, from GPS, GLONASS, Galileo, Beidou, and we can basically create the position of that satellite anytime. So if you want to kind of do a test in the past or a historical test and do something, last year, we can adjust the simulator so that the satellites are exactly where they were on that date and time. Or even if you want to simulate a mission in the future, we can actually put those satellites in the right position for next year, maybe on February 23rd at 5 a.m. So we can control the satellites, the messages, the information in the satellites, the actual location of the satellites. And then, of course, the signal, once it leaves that satellite, going through the atmosphere. As it goes through the atmosphere, controlling the atmosphere and creating different types of effects in the atmosphere, as well as to simulate the loss and that extremely long distance that signal travels. And then moving down to the third category, which is the location or the environment where you're testing. So this could be truly a space vehicle. Maybe it doesn't go through the atmosphere. Maybe it's in the atmosphere itself, or actually in low Earth orbit. Maybe this is an airplane flying through the air, or maybe this is a car driving through the city, which is what you see in the picture, where we can actually take something like a city or an environment, or maybe even in the mountains, and we can create that environment with lots of interference and noise, or maybe echoes or multipath, so that you have that full realistic environment that you want to test in. And then last but not least is the actual vehicle. Is this a car with one antenna? Or is this maybe an army vehicle or military vehicle with two antennas, or even an anti-jam antenna? Or even some type of environment where it's even a ship at sea. We create that entire environment for you, or realistic environment, so that when you connect this to a device, whether that device is something very, very, very simple, like a recreational type receiver or a sports watch, to a very, very complex system, normally in aerospace or in government or in military. But that device believes that it's in that place, that time, under those conditions that you need. And then you can control every aspect of that test, whether you want to send interference to it, whether you want to actually change the signal levels or see what happens if you start to lose satellite signals. So when we talk about test and simulation, we're truly creating realism, a realistic environment that you can control in 100% capability, and actually make sure that that receiver or that vehicle or that device is tested under realistic conditions, and not just tested one time, but tested many times to make sure that everything functions properly prior to actually using that device in the real world. But of course, it goes way beyond that. If we think about moving into the future, or moving into more modern applications, I should say, GNSS is just one signal. It's just one technology. Where we really focus a lot of our time is thinking about different types of signals or different type of capabilities, because very few devices just rely on GPS or GNSS anymore. So I've got some examples here that we'll run through. So a lot of devices in this very first bullet here are using other devices, other technologies. Maybe it's a car and it interfaces with a LiDAR or laser-based system. Maybe you're using inertial systems or IMUs, or different types of sensors that actually may be in a device or on a vehicle. So we actually can interface or work with all of those other technologies so that it's not just that single signal. And of course, other signal sources, whether that's the standard augmentation signals like SBAS or QZSS that David mentioned, but even looking at some of the other technologies. So for example, there's several technologies emerging in what we call LEO, or low Earth orbit signals. So maybe an example might be a signal from Zona or other technologies. But also other augmentation technologies like RTK, where you get a signal from other source to actually send correction data or verify that your location is correct, so that we get that high accuracy. In technologies like agriculture, we're getting clear down to very, very, very specific accuracies, down in the centimeter level accuracies, because we have these multiple signals and multiple technologies. But a couple of things that we really focus on too is we don't want to force you to use what we have. What we're very proud of in our systems is that we give you the ability to create your own signals. Those signals could be something specific, or maybe you want to take a current technology and modify it. So if you see down near the bottom of this bullets, you have one called KPS. This is an example of where South Korea is actually creating their own series of satellites that stands for Korean Positioning System. So you can build something that doesn't exist in our system, from the satellite itself to where the satellites are to the signal that comes out of those satellites. And then, of course, as part of that, we have the ability to allow you to build additional capabilities in through what we call plugins. And plugins are basically the ability to take our simulation engine and add something to it, to modify it through open source capabilities. So maybe it's something as simple as how you see the user interface, to actually interfacing other devices or bringing in other systems or connecting to other sources. So we allow you to take our software and all of the core capabilities, but we open up certain aspects and allow you to create on your own. And this is huge in education and research, because the goal obviously is to take it beyond what we have today and see what we can do in the future. And then last but not least in that top section is the ability to integrate with other systems. So for example, a flight simulator that is in place, you can actually take our simulator and give a flight simulator a live signal, a live location, a live information, so that when they're actually using the flight simulator, they have realism. And this is what we commonly call HIL, or hardware in the loop. Going one step further to the bottom, it's not just giving signals anymore. It's making sure that your device can handle interference, jamming, in real-world scenarios. As I'm sure many of you know, the GNSS signal itself comes from a very long distance. It's about 22,000 kilometers, I think, that signal travels from the satellite to the Earth. So a GNSS or GPS signal is very, very weak by the time it gets to the Earth. So because it's a very weak signal, most of us can see in the industry and read in the news, especially with, you know, the events going on in Ukraine and so forth, that there's a lot of signals being generated that affect GNSS. So whether that's something as simple as interference from other signals, and this could be a cellular site or even a radio system for a utility company or something that actually is leaking a signal, and that signal is actually able to interfere or cause a disturbance in GNSS. But also this concept of jamming. And jamming is not always intentional. Sometimes it's unintentional by something as simple as a taxi cab driver who doesn't want his boss to know where he is. He puts a jammer in his taxi cab, and all of a sudden he causes a disturbance in an entire area. But of course, there's malicious attacks and what's called spoofing, where there is an intentional attack in a certain geographical area or an intentional attack on a specific vehicle to make sure that it doesn't know where it is, where it diverts it in a different direction. And then last but not least is something called meakening, which is becoming more and more common by criminals, especially people stealing cars, where they want the car to think it's not moving, it's staying still, but it's actually being migrated or moved to another location. So these are all the things that we think about when we talk about simulation. It's not just GNSS, it's all of these other things that need to be verified and checked so that it's not just in a perfect scenario, but it includes other devices and it tests it in adverse or critical or situations where there could be disturbances. So let's talk a little bit about how this was done traditionally. I've been in test and simulation now for probably 35 years, but only the last 12 to 13 years in positioning, navigation, and timing. But for a very, very long time, this technology didn't advance. It was very, very hardware-based. There was one or two manufacturers that created solutions, and that was all. But now there's multiple options, and we're starting to get away from this. But these original systems were very hardware-based. And if you've done GNSS simulation for years, you understand that this was a very large hardware system. It was very power intensive. It was very noisy. And it took a lot of electricity to power this system because it might have been a system that were very, very large or very huge as far as one or two rack systems. But the software is also part of this. Some of this software on these traditional systems was old. It'd been around for 15, 20, 30 plus years. And the software itself actually was struggling to keep up with the demand of where we are. Secondly, it was complicated. It was difficult to use. A lot of menus, a lot of hidden menus, and the fact that all of the capabilities was not in one software. You might have to add 2 or 3 software packages to make it work. And of course, automation was important. So making that automation better was part of it, and running more than one test. We have situations now where we're dealing with multiple vehicles. So you'll see in a little while where might talk about drones or swarms, where there might be 5 drones that we're working with, and you want to give a signal to every drone simultaneously with a different position and a different trajectory. And then last but not least, the part that is always the most difficult is the price. It was expensive. So a lot of universities, a lot of organizations did not have these simulators. People that were doing research didn't always have the ability to test this. So that high cost, not just to purchase, but to maintain. And since it was very hardware based, you had to replace that system every 4 or 5 years with a newer technology that would do more. So what we started this revolution on was to really change that. We were the very, very first company through our system, it's called Skydell, to use the capability of modern computing and modern devices. So we use a term that we call software-defined architecture, or SDA. And basically what we're talking about there is really in those 5 bullet points down below, which is instead of using this dedicated processor inside a box, could we leverage modern software and put that on systems like Linux or Windows, so that it actually gave it the power of that modern system, of those modern operating systems. And then running it through a powerful CPU, of course, but then leveraging cards that are called GPUs or graphics cards or graphics processing units. And basically the ability to use these cards allows us to process a lot more data in more of a parallel manner. And Lisa's going to get into some details on this in a couple of minutes. But that's a lot of power. And more importantly, with these systems, you can upgrade the CPU. You can upgrade a computer. If you want to process more signals or more satellites or power more vehicles, maybe you want to do 5 cars simultaneously, then you can put in a more powerful GPU or graphics card or multiple GPUs. And again, Lisa's going to get into some details on this in a couple of minutes. And then have that information come out as what's called an IQ file, which is a data format just before it gets converted to an RF signal. And that that IQ file is actually something that we provide to our users. So if someone wants to go in and take IQ files or even import IQ files from other systems, this is a standard format that we export and import, or more importantly, that we send to radios or software-defined radios, as you see on the bottom right. So what that means is that there is a large variety of these radios in the market, ranging from very basic to very advanced. And instead of us creating these radios on our own and forcing you to buy all of this stuff, if you happen to have a radio from a company like maybe DECTech or National Instruments, then there might be the ability to use existing software-defined radios and actually run those instead of having to buy this huge box from us. In fact, you'll see in a little while, we allow you to build your own system since the core strength is in our software. So if we look at these two side by side, I think you guys get the general idea. This concept on the left side of having fixed or dedicated hardware. This is kind of an older way of doing things. Of course, we can do this, and we do have products that still do this. But you're talking about systems that are dedicated to maybe just GNSS. They have limited capabilities. Maybe they actually force you to purchase satellites or channels and actually send those channels out through more of an FPGA type of system. And again, you're talking about high cost, high maintenance, high support, and of course, replacing those every 3 to 5 years. Where we've tried to develop this concept of an open software-defined architecture, where we use devices that exist. Why should we try to create a system when there's devices out there that get replaced every several years that are powerful and give us more and more power every year? So that scalability, that flexibility, to be able to do quick innovation, to be able to do hundreds and hundreds of signals simultaneously. through GPUs, and of course, leverage the actual rapid innovation of radios and systems out there. And of course, the most important part that we love is on the bottom right. Why should we create everything for you? There are very great GNSS engineers and some great educational facilities and some incredible people out there that can create signals on their own, that can do their own research. So this concept of open source or self-development, where you can develop your own systems or signals within our system, is a very, very powerful capability that we're quite proud of. So of course, the system we're talking about is called SkyDel. And this is our simulation engine. This is the power of everything that we do is actually in the simulation engine itself. And there's a lot of bullets there that I won't read through right now because these are typical things you might see in GNSS simulation. But there's a couple of things I do want to highlight, is that everything we do, as you see in the software, is very easy to configure, very easy to use, very easy to learn. You can actually start simulating on our system in a matter of minutes once you start using it. So it's quite simple. And of course, we have many tools and devices to actually help you. But if you look at the third bullet here, we actually work with common languages. So we can take and import or export from something like Python or C# or C++, or work with LabVIEW. So you're not dealing with months and months of time to automate or to code or to get the system to work in a certain way, because we're using common languages that many people are good at using it already. So there's no proprietary automation stuff. What you do in our system visually actually can be automatically exported to something like Python. And of course, we can do this at 1,000 hertz. And of course, we do encrypted signals and EU signals and Y code and M code and all of the classified signals also. Some of the benefits that we talk about here, and I will not read these charts because I might bore you a lot, but there's advantages of software-defined architecture. And by the way, we will be sending you these slides right after the session. And if there's ever any questions, you'll be able to send those through the Profen team. The modern GUI, obviously that saves a ton of time and cost because you can learn it very quickly. The ability to bring your own hardware or build your own system is something that we'll really emphasize here in a couple of minutes. You don't have to buy our hardware. Our software is something that's available and you can purchase, but if you have your own hardware, you can use something that you might already have. For example, if you already have radios. And of course, everything we built is on what's called COTS or commercial hardware. So what we have inside of our box, we never hide the fact of what's inside equipment that we do build. And we actually make it publicly available. And of course, the open source plugins that we talked about. So I'd like to hand it over to Lisa so she can get into a little bit of the details of this software-defined architecture so that you can really help to understand how it works and how it functions. So Lisa, you want to take it away?
Yep, thank you, Rob. Yep. Hi, everyone. Good afternoon, and thanks for joining us. As Rob said, I'm going to go over the SkyDel software-defined architecture. So what do we mean when we say software-defined architecture? It's more than just using a software-defined radio. It's really the entire architecture of the system. So we look at SkyDel, we can break it down into 3 different parts. First, we do the raw processing of the data. So when you give us a scenario, we have to process where those satellites are, where they're going to be moving, how the vehicle is going to be moving. All of that raw computation is done by SkyDel and uses the CPU power of the computer that it's running on. So how many instances of SkyDel we're running, how many satellites we can process data for, how much data we can be processing in the background is all dependent on the CPU power. As an example here, we said all in view satellites. And on the next slide, I'll go over that a little bit too to show you the power of the software-defined architecture. But then we take all that raw data that we process and we send it over to the GPU. So when I say GPU, I'm talking about a graphics processing unit, and it's the same thing that you use when you're using a gaming computer or something like that. I'm not talking about anything different. It's still the same. It's just the GPU, using same thing they're using for like Bitcoin mining, things like that. So we use a GPU to modulate the signal to create, at that point, digital data. So that IQ data is digital format. And then we send it to our software-defined radio, which then converts that into analog RF. And then we have our RF signal that we're generating. So you can kind of follow SkyDel through. And the nice thing about it is we're also able to up any part of the system that we want to. So if we need, more processing power, we can add additional CPU power, additional computers. If we need more GPU, same thing, add more GPUs. You can go on the next slide, Rob.
Mm-hmm.
Here I threw in a slide about all-in-view satellites and what does that mean? Because if you've been working in this industry for a while, or even doesn't even have to be that long, a lot of times we're talking about buying channels. So even with our older simulators, our maximum number of satellites or maximum number of channels that we could buy was limited to 64. And that was a limitation by the FPGA channels that we had available. Of course, we can use more powerful FPGAs, and we can, continue to design new hardware to use newer designs of FPGAs, but it doesn't scale as well when we look at how different the world is today than it was 10 years ago as far as available satellites. So I just picked a date and time and a location. And so this is all the satellites in view in the date, no time, and time and location. We can see there's multiple satellite systems, and this is only the 4 main systems. I didn't include S-band systems, any multipath signals. So even just to have the sky view without any additional signals that you might want to add or impairments that you might want to add, it's 179 signals. So in a traditional model that Rob was talking about, that would mean you need 179 channels. And if you didn't have enough channels in your FPGA, means you need to upgrade to a whole new hardware platform. New hardware is needed, and you need to replace. It's not scalable like the software-defined approaches. So I just wanted to ensure that we see the impact of that. When I say all-in-view satellites, we mean we can generate a lot of satellites, and that's very realistic because there are a lot of satellites out there today in the live sky. So we can go to the next slide. So back to this one, still looking at the same way, we're using SkyDel, then we're using a COTS GPU, which like Rob said earlier, COTS is a commercial product, stands for commercial off the shelf, meaning anyone could just go buy it. You don't have to be a special user, have special, there's no special restrictions for you to buy it. I could just go to the store and buy this type of product. So we use COTS product for the GPU and COTS product for the SDR. Then of course, SkyDel, we run on a computer, which is also a COTS product, but SkyDel is our focus. So we don't focus on developing the GPU or the processing hardware or designing FPGA boards. We focus on the software. So we can put all our efforts in designing the software and let the guys designing the RF hardware, design newer, better software-defined radios, let the GPU manufacturers design better, faster processors, and we'll focus on what we're good at. We'll focus on the SkyDel software and GNSS simulation and just take advantage of the work that the others are doing in these areas. So earlier I was mentioning about scaling. So this is one of the benefits of the model that we use, the software-defined architecture, is the ability to scale. Since we can really relate one-to-one, the SkyDel uses CPU, modulation uses GPU, RF is done by the software-defined radio, the conversion to analog. So if I need more processing power in Skydell, I can add power there. If I need more GPUs, I can add another GPU in my system. I don't have to purchase a whole nother system. And in this case, you see, I needed more outputs. I wanted more radios. I wanted to do GNSS on L1 band, GNSS on L2 band. Then I also want to have jammers available on the L1 band and L2 band, because maybe that's the purpose of this simulation, is to have jammers. So that I don't need more processing power for that. I don't need more Skydell instances for that. I need more software-defined radios for that, though. So I can just scale just that part of the system. I don't have to buy more boxes in order to add that capability. So then on the next slide, we can see that we can do this kind of scaling in all areas, right? So we need more Skydell, more satellites, a different trajectory, multiple vehicles, whatever the case is, running more than one instance of Skydell. But we can still use the same GPU if our instances that we're running are not using very much of the GPU power that we have. We can still use the same GPU. We don't have to scale that part of it up if we don't need to. And then when we're ready to, we can. So when we go on the next slide, you can start talking about how we could, though, scale up the GPU if it becomes your bottleneck, right? So now you have this set up and you start running it, and we have tools in Skydell to show you the performance of how each of these workers are doing, so that you can tell when you're running to the limit of what the system can do. So here, this GPU becomes a bottleneck. We add another GPU. We don't have to buy a new simulator. We can actually just, go online, buy a computer gaming GPU from NVIDIA and add it into the simulator, and you have more modulation power. It doesn't have to come back to us. It can be. Now, we can also take care of the hardware part of this for you, but it doesn't have to be. Our focus is the software, but we can also put together commercial off-the-shelf systems that we call turnkey solutions. Okay, and the next one. Just looking at the GPU performance criteria, I added this slide in here just so you have this as a reference, but I'm not going to go over all of the different types here, but just know that the type of GPUs that we support are the NVIDIA GPUs. So we only support NVIDIA GPUs because we use their CUDA core language, and that's an NVIDIA proprietary language. So CUDA is the language you use for the GPUs, so it's proprietary to NVIDIA. So we can get professional version and commercial version GPUs from NVIDIA. The thing I'd like to point out here is that the commercial version and the professional versions of them have the same performance. It's really the total number of CUDA cores for Skydell that matter. The professional version we use in our turnkey systems because we need to have like life cycle management. We can't just go to the store one day and there's no more GPUs, right? As a professional product, we need to pay for the professional versions, which will let us know ahead of time when it's going at end of life, and work with us to maintain a product. So the commercial versions of these work just fine as well. It's really this total number of CUDA cores that Skydell uses. That's the number that matters, not whether it's a professional grade or not. So just the architecture and the number of CUDA cores are the things that matter. And then if you kind of in your head are thinking, how many signals can I make? Because you got to have some kind of benchmark. We don't do channels like a traditional FPGA, but you have to have some type of way to know what type of power we need. So we say our rule of thumb is for each signal, you need approximately 16 CUDA cores. So some signals.
There's a question.
Yes.
Maybe it's time to answer here. Is Skydell supporting Mac OS too? Or friends from?
So it's not supporting the Mac OS, only the Ubuntu Linux and Windows 10.
Okay.
Today.
Thank you. You can go.
So yes, this is what you need. So you can use that. Some signals will use less than 16, some will use more. It's more of an estimate, but it will give you the a good way to do the estimate if you already have a GPU that you want to see how it can perform in SkyDel. There's a benchmark tool in SkyDel you can use, but that of course requires already having the GPU. So you could look at it, you know, estimate ahead of time, or use the performance tools in SkyDel to see how many signals you would be able to make. So you would go to the next slide. And with that, I'm turning it back over to you, Rob, to talk about how SkyDel is unique.
Thank you, Lisa. So we're a little bit behind schedule, but I think we're okay. So I'm going to keep moving on. So as Lisa mentioned, as I mentioned earlier, we offer the ability to give you a complete system. So as you see on the left side, we can give you the SkyDel simulation engine, but we actually have products, hardware products, and this is one called the GSG8. But like we talked about, this is truly just a computer with a strong CPU with a specific quantity of GPUs and radios or outputs based on your need. So we configure this box specific to each customer based on the quantities of what they need. But if you look at the right side, excuse me, we also allow you to build your own system. So it's still the same SkyDel software engine, which is where we get our power from. But if you want to run your own computer, you want to use your own GPUs, and you want to use your own SDRs, you can build your own system, and we provide all of the specifications for you. So you know basically how to build this. And of course, our team is always willing to help you to build your own system. There is a family of products that we have. You'll notice that on the left side, there is a product family that does not use the SkyDel simulation engine. This is what we call our traditional simulator. This simulator has been around for 15 plus years, and it's a very simple simulator. But all of our newer simulators that we're creating are based on this new software-defined architecture, where SkyDel is the core of itself. So SkyDel can be used without hardware. So if you're dealing with students or someone that wants to just use the SkyDel engine, I'll talk about our academic program in a little while. You can use SkyDel by itself on a computer. But of course, if you want to actually run very basic applications, you can run on what's called our Solo product, or some of our newer products, which are more commercially based, which is GSG7, to our advanced simulator that can actually do 4 outputs simultaneously, or even clear up to our classified signals, which is the blue box, or even use multiple boxes or multiple solutions to be able to actually transmit inside an anechoic chamber. So maybe you have 18 or 24 antennas inside a chamber. We can actually create a system that actually sends GNSS through all of those 6 antennas simultaneously to get your angle of arrival. And then, of course, for military and high-end defense systems or anti-jam antennas, and we commonly call those SERPA or wavefront systems, then we can give very, very advanced systems. But the important part of this, no matter what, is that everything runs on SkyDel. So if you actually start with a very basic system today, but you want to actually use it on an advanced system next year, the software is the same software. We don't have different software versions and different variations like other manufacturers. We like to have one software engine, and we configure it based on the use case. There's a lot of unique capabilities. I'm going to send you this chart so you can actually see some of the unique things that we do. But I do want to highlight a couple of quick things. Lisa mentioned all in view, which is the second item. We don't charge you for that. We don't make you pay for channels. Every other company that offers simulation, they charge you like $1,000 per satellite. We give you all in view because we leverage the power of the GPU that Lisa talked about. And if you do automation, the third item, I can tell you that our automation can be done in minutes, where actually a lot of our competitors could take hours, if not weeks and days. and of course the open source plugin. But I will send you these slides and you can read these in detail so that I won't put you to sleep on Wednesday. So last, I want to talk through a couple of use cases, and Lisa and I will probably go through this together so you can kind of run through it and understand it. It's understandable that you can see our architecture, but I want to kind of put some realism to that so you can see what we mean. So of course, our simulators work in manufacturing. So if you actually want something very quick at the end of assembly line, then it's a very simple simulator. If it's research and design, then you're dealing with products that typically are more complex, that are typically used early in the design phase. Clear up to advanced systems. So in advanced systems, you might be dealing with a high-end SERPA or wavefront system. You might be dealing with encrypted signals. And of course, a lot of things that go way beyond that, not just the advanced capabilities. But let's get a little bit more specific. So maybe Lisa, do you mind talking through this multi-vehicle scenario for the attendees?
Sure. So this is a good example of what we can do with the multi-vehicle. So when we look at Skydell, we call Skydell the simulator. And what Skydell's running on is just its hardware, right? So we can run multiple instances of Skydell, and we would be considering calling that running, 2, 3, 4 simulators on one set of hardware, right? And that's what multi-instance or multi-vehicle is having one set of hardware that you can use those radios in there for different instances or different simulations. And when you think about it, in a system like GSG 842 with 4 radios in it, each of those radios can operate as an independent simulator. So we can have, in this case, the master being the base station, and then we have, 4 rover slave instances open, but these can all be running on one computer, or you can have 5 different computers. Skydell can use its master slave functionality over a network or on one computer, so it doesn't matter to Skydell. Obviously, you optimize your network for latency and stuff, but it doesn't matter if you need more processing power for each instance. You might want to go with separate computers with more GPU power. If you doing, you want a lot of instances, but you just need a couple of GPS L1CA signals, just a few signals just to get a position fix, then you're not using very much power of the signal. So you may as well run them all on one computer. Doesn't even need to be a very powerful one for that use case. So it's something very different than anything that could be done in previous versions of simulators that were hardware defined. All right, you couldn't turn one system into as many simulators as you want, right? We have customers, this example, I had used one of our turnkey products, but we have systems with customers out there that have 16 outputs that actually have, 32 outputs when you look at it dual frequency way. So we can have a lot of Skydell instances master slaved together and to make bigger systems that scale nicely and make multi-vehicle simulations with just one simulator. And you can go on the next one. I think it's a more example of the same. So it's showing you now, you can run a single instance on, our GSG 8 with one RF output and one GPU. So that's what we call our GSG 811. So maybe that one has enough power and enough everything that you need, processing capability to put out a PVT solution or provide satellites for a PVT solution for one drone. Maybe you are using all in view satellites and you need 200 satellite signals for one drone, right? So but now you want to do 4 different drones. You want each of them to have a different PVT or position, velocity, and time. Now we can say, oh, well, now we just have to say on that same piece of hardware, we can just add 3 more radios and a GPU, and now we can run 4 instances on that same box. So you're not taking up any more space. You're not purchasing unnecessary pieces of the system that you don't need. You're only scaling up the places you need to scale up, which in this case, we need more RF outputs and we needed more GPU power. So that's what we scale up. We don't need to add multiple boxes every time we want to add more capability to the system. And then the second use case I had here was for testing these controlled reception pattern antennas in a controlled environment. So a lot of times you hear Rob will use the term SERPA. So CRPA, that's what we mean when we say SERPA. A lot of times we also will use the term CRPA. But to test these systems are military systems designed to detect the angle of arrival of a jamming or interference or a threat signal and create a null in that direction, basically attenuate the interference signal and allow the rest of the system to continue working. So in order to test those, we can't just plug in a conducted cable because we have to actually have some directionality to the signal so the system can work properly. So there's two ways that we do that. We do that in, well, the two ways we test it in a lab. Of course, you can test it in a live environment as well. We can do it over the air in an anechoic chamber, or we can do it completely cabled where we generate all the signals and all the interferences for every element, but they would be directly cabled into the elements, and that we call the wavefront simulator. So we can test over the air or conducted for the big CRPA test systems. So that's kind of like two use cases where SkyDel really, that scalability of SkyDel really comes into play, where we can, add the capability where we need it. If you start with a smaller chamber, grow it to a bigger one, or you want, more antennas in that chamber, whatever the case is, where you design a system to be scalable all the way from the smallest BroadSim Solo that you saw, the small little one that Rob showed briefly, all the way up to the big systems. We want to make sure that everything's scalable and everything's running the same SkyDel software, so that when you're familiar with one, you're familiar with all. You can go to the next slide.
Good.
And this is just, real pictures of those systems, because I had to throw them in there because they look nice.
They look pretty. Exactly.
But they're the
They
same
are
systems.
like Minecraft game.
Yeah.
Exactly.
Exactly. Yeah.
So as we start to wind down near the end of this, we've talked about the products. We've talked about SkyDel. We've talked about the architecture. But I do want to talk about a couple of more things before we open it up for questions. We actually want to create a different environment. And I apologize, there's actually a misspelled word that's supposed to be SkyDel promotes global collaboration. That extra T should not be on the end. But there's several things that we do because we believe that we should grow as a community. Research and design, education of GNSS and positioning, navigation, and timing is important to us. So there's a bunch of things that we do that are quite different than other companies in the industry. The first one is we actually have a program called Orolia Academic Partnership Program. For universities and education organizations that qualify, we actually donate a SkyDel simulation system. We actually have done this now for over 55 universities across the globe. And what we're trying to do is build a research program where if you're working on anything from an autonomous vehicle to creating atmospheric models for scintillation or whatever, maybe you're trying to create a brand new signal or do research on low Earth orbit, we actually do donate our SkyDel simulation engine to universities. And that's typically one site license or one permanent license, as well as the ability for student licenses. So if this is something where you think it can actually help your curriculum or help your research, reach out to the Profen team. Let's set up a discussion. Let us understand what you're working on. And if you do qualify, we actually do donate that software to you, and we add you to this network of universities. And I actually will put the link in the chat windows during the question session. You can actually go on Orolia and look at this program, and you can see the network of universities all around the globe. We're very proud to say that that is in over 55 universities in North America, South America, Europe, Africa, as well as Asia and Australia. So these are actually a lot of universities across the globe. And if you actually like autonomous vehicles, we're actually sponsored a lot of the vehicles that are actually going to be in the race in Las Vegas. A lot of those vehicles were tested by Skydell, and it's going to be autonomous vehicles as far as racing teams. Of course, we actually like to have as much information out to the public. So since we do offer open source, we have a ton of tools, a ton of resources, a lot of information on our online forum. This is called learn.orolia.com. And again, I'll try to put that in the chat window during questions. This is basically where you can go and you can look at what research is being done. You can look at white papers from us, as well as research papers from some of the universities and people that are doing work. We've got a GitHub repository where we actually share our code. We publish information out there. And of course, our technical team stays on this system all around the globe. So you can ask questions at any time without having to pick up the phone or open a trouble ticket. You can get access to experts immediately. And of course, this open source development and sharing, the plugins, the custom source, our custom signals, these are all things that we're quite happy about. There are many plugins and open source tools that have been developed by universities all around the world. Some of those are published. Some of those are just used by the university or more private. Because if you develop a plugin, we don't own that. You own that. So a lot of things you can do are stuff that even you can publish yourself to do additional capabilities. And of course, there's a ton of systems out there, so I'm not going to read these. This is not a new system. There's thousands and thousands of Skydell systems out there. There's thousands of systems. There's major projects that you can see that are announced. So this is not some small company or some small system. This is a very well accepted, a very strong system that is actually used from military applications clear down to even, like I said, recreational companies or even chipset companies. So at this time, we'll open it up for questions. You guys can type in some questions into the window. And a couple of these were already addressed, but maybe we'll address them again. So Lisa, one of the questions that came up was how many satellites or channels can a GPU support? And we see this quite often. It's a common question. It depends on the GPU, of course, but maybe you can talk a couple minutes about that question about how many satellites can a GPU support and maybe review it for a minute.
Sure. So the GPU selection is going to be based on the number of CUDA cores that the GPU has and the GPU architecture. So this we have a guide for you for GPU selection that can like help you to determine what would be good for suitable for your needs. But the general rule of thumb is 16 CUDA cores per signal. If I took a look at it and I said, okay, I only wanted to make the simplest signal like GPS L1CA, I just wanted to make, hundreds of those, then it's going to be less CUDA cores than 16. But then there's signals that are going to take more than 16. So 16 is just a kind of rule of thumb or an estimate if you're trying to decide on a GPU. If you already have the GPU, though, we do have some profiler tools in Skydell that you can run that will let you know the capability of your GPU, what it's possible to do with it.
And I just entered the online forum. It's learn.orolia.com in the chat window. And I'm actually just now typing in the link. It's orolia.com/OAP for the academic program where you can see the list of all the universities.
So I think, I'm not sure, Rob.
Did I type it wrong, Lisa?
Well, I just don't know if you're sending it to.
It says host. Oh, it says host and panelists. Actually, I sent it to the wrong place.
No, but I don't know if you can. I think the owner has to do it.
Yep.
But we can move on to the next question while we figure this out. There was another question about Skydell supporting Mac OS. So it does not support Mac OS today. Original version of Skydell did support the Mac OS, and that was, dropped about 3 to 4 years ago. I can't remember exactly when, but that was about when it was dropped. The reason we dropped the support for it was because Apple stopped using NVIDIA GPUs and developed their own. So you may be familiar now that Mac, Apple, make their own chips and now GPUs and everything, the M1 chip and the M2 chips. So they stopped using NVIDIA GPUs. Our requirement of our system is an NVIDIA GPU. Therefore, we no longer supported the Mac OS because their systems were not supporting the NVIDIA GPUs. But you might, use Google and find some reference somewhere to Mac OS because we did support it at one time, but that was years ago and it's no longer supported.
So to the Profen team, I tried to post the link to the window, but I think it's just to you guys. Can the Profen team maybe publish the learn.orolia.com for the learning forum and the orolia.com/OAP?
Yes, we will post it.
It did.
Perfect.
Yeah. It's there now. Everyone should see that.
A personal question to both of you. Why did you choose this area, this time, place, simulation area? Rob, you are very experienced in this area. And what do you advise to the students, university students that want to study in this area?
It's an interesting question. I actually started off in the military as a technician and an engineer. And then I went into test and measurement for telecommunications. So I did fiber optic system, telecom systems, cellular systems, Ethernet systems for probably 15 years. But I actually found it kind of boring because it was testing to standards. So I moved to GNSS about 12 or 13 years ago. And I moved to GNSS because it looked fun. Every day I deal with an application that is interesting. Like one day I might be dealing with a sports watch. The next day I might be dealing with a customer who has jamming coming into their GNSS system in Finland. Another day we might be dealing with airplanes. So every day my day is so cool because it's not just technology, it's how it's being used. It's what's a customer doing with it. Or more importantly, a really cool research project that a university is working on that's something I never thought of before. So I think it's so much fun to deal with something that we all see as a simple technology. We all use GPS, we understand it, but wow, so many things that we can do with it, and then testing it to be able to create that environment. It's so incredible and I love doing it overall. So I think Lisa, you probably have a slightly different story, but similar start.
Yeah. So I also was in the military, the U.S. military for 10 years. I was a radar systems technician and then instructor. So I was able to learn a lot about radar systems and RF from there. So when I got out of the Navy after 10 years, I worked for 1 year at another company, and then I joined Orolia. So I have not done much other than working with Orolia, but immediately the reason they were hiring at the time is they had acquired a company that brought the GNSS simulation into Orolia, which at the time was Spectracom. And so I became the default person for everything related to that company. So I had to learn the GPS and GNSS stuff very quickly. And like Rob, I found it really fun and interesting and challenging. And I love it when Rob, he finds the fun applications, then he throws it over to me. Can we do this? And then I'm like, well, let me try it. I don't know. We haven't tried everything. So it's always fun to, try different things and stuff too. So
and you are both of you learning new things, right?
Yes, all the time.
And if there's students online, we are always hiring. So that forum, there's always published jobs on there, not just for us, but for Qualcomm or Samsung or SpaceX. So we're always hiring, and companies are always hiring in this market. So I don't
David,
think.
Do you have
there was
anything
any
to
more...
say about this sector?
Yeah, likewise, I think it's really exciting. You know, and we have quite a wide. I tend to work with some of the other portfolio products, but to be honest, simulation is, as Rob says, it's the applications which are really exciting, and seeing some of the innovation that our customers are doing really spurs us on to you know, develop new applications and features. That's really, yeah, it's a really interesting field to work in for sure.
Thank you for your time, Rob, Lisa.
No problem. And I
David.
just put a couple of links up on there. There's the forum. I actually dropped that slide in there really quickly. So there's the learning forum. There's some data sheets. There's some videos overall. But maybe I can actually just comment really quickly and say thank you to everybody who attended the seminar. We love doing these seminars. I mean, it's a little bit early in the morning here in the US, but it's still fun doing these seminars. So if you guys want more seminars, more learning, more specific information, go to the Profen team. But from all of us at Orolia, we sincerely thank you and appreciate you taking your time to spend with us this morning.
Thank you all for your time. Değerli katılımcılar, bir teknoloji günlerinin daha sonuna geldik. Bugün Orolia firmasından Robert Burke, Lisa Perdue ve David Godwin'i dinledik. Çok güzel örnekler verdiler. Önemli olan yerimizi, zamanımızı ve lokasyonumuzu bulmak için çok güzel bir çözüm. Skydel'de öğrencilere ve akademisyenlere çok güzel olanaklar sunuyor. Bir sonraki teknoloji günlerinde buluşmak üzere. Hepinize iyi günler diliyorum. Thank you all. Bye.
Thank you. Bye-bye.